In this deck, we cover the storage location assignment problem, often abbreviated as SLAP. The core decision is how to assign products, also called stock keeping units, to specific storage locations so picking work is fast, reliable, and safe. We will build a complete story from a mathematical baseline to practical heuristics, meta-heuristics, machine learning, and system-level digital twin and governance ideas, ending with practice questions you can implement. Order picking is often the single largest cost driver in warehousing, and in many operations it can reach up to 50% of total operating expense. That means storage placement decisions show up repeatedly in labor cost, equipment utilization, and customer lead time. A weak assignment becomes a recurring penalty. Every order forces extra walking, more congestion, and more handling touches. A strong assignment reduces travel and makes the entire operation smoother across thousands of picks. The scenario is a pharmaceutical distribution center operating at large scale. It handles roughly 10,000 stock-keeping units across about 15,000 storage locations. High-velocity medications must be placed for rapid access, but placement also has to respect temperature zones and regulatory compliance. This makes the problem more than just putting popular items near the front. SLAP is difficult because you must consider multiple drivers at once. Demand velocity and seasonality change over time, and product size and location capacity limit what can physically fit. In addition, product affinities matter because items frequently ordered together should be near each other to reduce cross-aisle travel and congestion. You also have accessibility and equipment constraints, so the best theoretical location may be operationally inconvenient. We use a tier structure to organize solution approaches. Tier 1 provides a complete mathematical formulation that acts as a gold standard baseline. Tier 2 adds a fast savings-based heuristic. Tier 3 adds a population-based Moth-Flame optimization search. Tier 4 introduces a variational autoencoder learning approach. Tier 5 and Tier 6 move into digital twin and multi-agent adaptation. And Tier 8 adds value-aligned governance. Tier 1 frames storage assignment as a structured optimization problem. Each product must be assigned to exactly one storage location, and the assignment must respect capacity limits. The objective is to minimize handling effort, which is driven by travel distance and pick frequency, while also accounting for the operational cost of separating products that have strong affinity with each other. This slide defines the basic sets used by the model. There is a set of products, a set of storage locations, and a set of affinity groups. These sets are the vocabulary of the model. They let you express placement decisions, group-level policies, and the structure needed to measure both travel cost and affinity-driven interaction effects. Products represent stock-keeping units that must be stored and later picked. Locations represent bins, shelves, or automated storage positions in the warehouse. Affinity groups represent clusters of items that are frequently ordered together. Modeling these groups helps you reduce cross-aisle movement and congestion by encouraging co-location or near-location. This slide lists key parameters that quantify the warehouse environment. Distances to the input and output point approximate travel time and effort. Velocities represent how frequently products are picked. Space requirements and location capacities represent physical feasibility, and affinity scores capture the strength of co-pick behavior between products. Distance is a proxy for walking time, vehicle time, or automated travel time, depending on the facility. Velocity turns distance into expected repeated effort because a popular item creates cost again and again. Space and capacity keep the plan physically possible. Affinity captures co-pick behavior that influences real congestion, so the model can prefer layouts that reduce back and forth travel across the building. This slide introduces binary decision variables that represent assignment decisions. For each product and each location, the variable indicates whether that product is placed at that location. A second binary variable indicates whether a given affinity group is activated. This gives the model a way to represent group-level placement policies and their associated penalties. If you do not enforce binary assignment variables, an optimizer can produce fractional placements that are not implementable. Operationally, that would mean a product is split across multiple bins in a way that does not match the intended policy. The group activation variable supports explicit trade-offs. It lets you represent when you are willing to pay an extra penalty to keep related products together versus when you prioritize pure distance-based travel reduction. This slide shows the objective that combines direct assignment cost with a penalty linked to affinity group activation. The direct cost captures travel distance multiplied by pick frequency. The affinity term reflects the operational pain of separating items that are often ordered together. Together, the objective formalizes a realistic trade-off between short travel for single items and smooth multi-item picking patterns. The first term is the cost you pay repeatedly during picking. High-velocity items placed far away create constant wasted travel. Minimizing this term pushes popular items closer to the input and output area. The second term acknowledges that orders are not independent single-item events. If you split strongly related products across distant areas, you create extra cross-traffic and congestion, so the penalty discourages that pattern. This slide enforces that each product must be assigned exactly once. It guarantees every stock-keeping unit has a defined home location. Without this constraint, a solution could omit a product or assign it to multiple places. In practice, that would break inventory integrity and confuse both the warehouse management system and the pick process. A warehouse needs a single source of truth for where each product lives. This constraint ensures that the assignment plan can be implemented and audited. It also prevents a subtle failure mode where the model lowers cost by implicitly ignoring hard-to-place items. By forcing every product to be placed, the plan stays realistic. This slide enforces capacity. The total space requirement of products assigned to a location must fit within that location's capacity. Capacity constraints are crucial because ignoring them produces plans that look optimal on paper but are impossible to execute. They protect physical feasibility and help avoid overflow and unsafe storage conditions. Locations vary in size and in what they can safely hold. A correct model must prevent overstuffing a bin or assigning oversized items to unsuitable storage. Capacity limits also reduce downstream handling. When locations are overfilled, replenishment becomes harder, pick errors increase, and congestion grows. This slide introduces a coverage-style constraint tied to affinity groups. Conceptually, it links how products in the same group are placed relative to distance. The practical purpose is to encourage group-level co-location patterns so that multi-line orders can be picked with fewer cross-warehouse trips, reducing travel and congestion. If you only minimize distance individually, you can end up scattering a frequently co-ordered set across multiple far-apart areas. That increases travel and creates repeated crossings through busy aisles. The affinity coverage mechanism prevents that failure mode by making it costly to separate group members, unless there is a strong reason to do so. This figure provides a visual intuition for the Tier 1 formulation. Products are assigned to locations, and the goal is to minimize the total cost that combines travel and affinity effects. Use the figure as a bridge between the abstract model and the real physical layout. The same decisions appear as actual bin placements that shape daily picker movement. This slide presents a small concrete example with 3 products and 3 locations. Product velocities are 50, 25, and 10, and the location distances are 2.5, 4.2, and 6.8. From these values, you can compute an assignment cost matrix. The example shows how the cost scales with both distance and velocity, which is why high-velocity items should be placed closer. The example assignment places product 1 at the closest location, product 2 at the middle location, and product 3 at the farthest location. This produces the minimum total cost under the simple assumptions in the example. The slide also shows how the total is computed as the sum of the chosen entries, yielding a total cost of 298. This makes the objective concrete and testable. Tier 2 introduces a classic savings idea adapted to storage assignment. Instead of solving the full optimization, you estimate how much you save by placing 2 related products together. You then prioritize pairs with the largest positive savings. This creates a fast, constructive plan that is often good enough when you need rapid reslotting. This slide defines savings as the difference between placing items independently and placing them together. If co-location reduces total travel cost and captures affinity benefits, savings is positive. Savings gives you an operational rule for which items to group. It is intuitive for practitioners because it mirrors how experienced planners think about co-picking and travel reduction. The stated time complexity is roughly quadratic in the number of products, plus the cost of evaluating candidate locations. That is a practical runtime for many warehouses, especially compared to exact optimization. Operationally, this makes the approach suitable for fast replanning during peak periods or when demand shifts quickly. This code slide shows how savings are computed between product pairs. It calculates individual placement costs and compares them to a joint placement cost that can include an affinity bonus. The key idea is that you compute a numeric score that tells you whether grouping is beneficial. This supports a greedy but structured construction process. This part shows how savings values are pushed into a priority structure so the algorithm processes the best opportunities first. That prioritization is what turns many pairwise scores into a coherent assignment. It also introduces assignment tracking and location usage tracking. Those bookkeeping steps are essential to keep the heuristic feasible with respect to capacity. This part shows how the algorithm selects the best feasible location for a pair and commits the assignment when it is beneficial. Then it assigns remaining products to the best remaining feasible location. The main operational point is that feasibility checks happen at every step. That keeps the plan implementable even though the method is greedy. This diagram summarizes the flow. Compute savings, sort or prioritize, assign pairs, and then fill in remaining assignments. The loop captures how the heuristic constructs the plan incrementally. Use this diagram as a mental model for implementation. It highlights where you would plug in business rules, such as zone restrictions or temperature constraints. This slide provides a concrete reported outcome for a small dataset. 4 products with velocities 50, 30, 20, and 10 are assigned across 3 locations at distances 2.0, 4.0, and 6.0. The reported result groups products 1 and 2 at the closest location, then assigns products 3 and 4 to the other locations. The slide reports an 18% total cost reduction compared to a naive assignment. Tier 3 introduces Moth-Flame optimization, a population-based meta-heuristic. Candidate assignments are moths, and the best solutions found so far are flames. The algorithm updates moths by spiraling toward flames while still allowing random exploration. This helps search a large assignment space without requiring full exact optimization. This slide defines a fitness concept that combines travel cost with an affinity penalty. Lower fitness means a better assignment. The key is that the fitness function is where you encode operational priorities. If you want stronger affinity preservation or stricter congestion control, you increase the penalty weight. This code slide outlines the Moth-Flame optimization class structure. It defines problem dimensions, population size, and iteration count. The operational takeaway is that population-based search gives you a tunable quality versus time trade-off. More iterations and a larger population often improve results but cost more compute time. This part shows how an initial population of random assignments can be created. Random initialization provides coverage of different parts of the search space. The algorithm then evaluates each assignment using the fitness function. That evaluation step is what connects the meta-heuristic to real operational costs. This part shows the fitness evaluation idea. Some travel cost for each product location placement, and add penalties when related products are separated. This is the most important implementation step. If the fitness is poorly designed, the algorithm can converge to solutions that look good numerically but fail operationally. This part shows the spiral update rule that moves a moth toward a guiding flame, with a decreasing exploration factor over iterations. That structure encourages exploration early and exploitation later. It also shows how improved moths can replace flames when they achieve better fitness. This best so far tracking is what drives convergence. This figure visualizes the Moth-Flame search process. It helps you see how candidate solutions move around the solution landscape and gradually concentrate near high-quality regions. The picture is also a reminder that meta-heuristics do not guarantee optimality, but they can deliver strong, practical solutions when exact optimization is too slow. This slide reports a concrete example. 6 products with velocities 45, 30, 25, 18, 12, and 8 are assigned across 4 locations at distances 2.0, 4.5, 6.0, and 8.5. The reported result converges after 150 iterations, with total cost $384.50. It reports 23% improvement over random assignment and 8% improvement over a greedy heuristic. Tier 4 shifts from search to learning. A variational autoencoder learns latent representations of good storage assignment patterns from historical data. The idea is to generate assignment candidates that already resemble effective layouts. This can reduce search effort and help adapt quickly when demand patterns shift. This slide shows the learning objective as a combination of reconstruction loss and a regularization term that shapes the latent space. Reconstruction encourages the model to reproduce good assignments. The regularization term encourages smooth, generalizable latent structure, so the model can generate new solutions rather than memorizing training cases. The model input combines product features and location features. Product features include velocity, size, category, and fragility, while location features include distance, capacity, and zone attributes. Historical assignments provide supervision signals and patterns. This lets the model learn what good layouts look like under real operational constraints. This code slide defines the overall variational autoencoder structure with an encoder, latent variables, and a decoder that outputs assignment probabilities. The key takeaway is that the model maps a complex warehouse configuration into a compact representation, then reconstructs a plausible assignment from that representation. This part shows how the encoder produces latent distribution parameters and how the model samples from that distribution. Sampling enables generation of multiple candidate assignments. Operationally, sampling is useful because you can produce several alternatives and then select the best one using feasibility checks or a downstream evaluator. This part shows how the decoder produces assignment probabilities and reshapes them into a product by location structure. That structure is a bridge from machine learning output to a discrete assignment. A practical implementation step is converting probabilities into a valid one location per product plan while respecting capacity and zoning constraints. This part shows a training loop concept with an optimizer and a loss function that combines reconstruction and regularization. Training uses historical assignment data. The operational point is that the model is only as good as the historical data quality. If past assignments were biased or constrained by hidden factors, the learned patterns will reflect that. This part shows how to generate a new assignment by encoding features, sampling in latent space, decoding probabilities, and selecting the most likely location per product. In practice, you would validate the generated plan and, if needed, repair it to satisfy hard constraints like capacity and temperature zoning. This figure illustrates the encoder, latent space, and decoder flow. It visually explains how the model compresses and reconstructs assignment structure. Use it to communicate the approach to stakeholders. The diagram makes it clear that the model learns patterns, not explicit rules, and that it must be validated. This slide reports training on 1,000 historical assignments. The reported outcome is 15% better cost efficiency than a random assignment baseline. For a test case with 8 products and 5 locations, the reported generated assignment has reconstruction confidence 0.87, and it captures the pattern of placing high-velocity items near the input and output point. Tier 5 introduces a digital twin that keeps SLAP continuously up to date. Rather than treating assignment as a one-time project, the twin treats it as an ongoing optimization cycle. The twin integrates sensor data, warehouse management system signals, and predictive analytics. It evaluates multiple scenarios and recommends changes only after simulation-based validation.